Hi everyone, today we start with a new video on Newtonian gravitational force, and the title of the video is Angular Momentum. So the problem originally is we have two masses, mass number 1 and mass number 2, located in space, and the force between them is an attractive force which is given by the Newtonian gravitational law. Now there are two forces in the problem, action and reaction forces, and what is important is the vector that's connecting mass 1 to mass 2, and that what we call vector r, which is equal to position vector r2 minus position vector r1. Now in the previous video we reduced this problem, which is called a two-body problem, into one-body problem by simple mathematics, and we proved that the problem is equivalent to a new mass, a new object of mass called the reduced mass, and located at the with the position vector r. Today we will continue talking about Newtonian gravitational force, and we will talk about one quantity that plays a very important role in the discussion of Newtonian gravitational force, and this quantity is the famous angular momentum. Now let's imagine we have a mass of mu, that's the reduced mass, located at position vector r, and it carries a velocity v, and there is an angle between the direction of r and v, we call it theta. So now what is angular momentum? Angular momentum about the origin is defined to be the position vector r cross product with the linear momentum vector, and you all know that linear momentum vector is simply the mass times the velocity of the object. Now, we know also from a cross product that the direction of the angular momentum is always perpendicular to the two vectors r and linear momentum p, which means angular momentum is perpendicular to the plane in which r and p exist. So in this, if you look at the picture, then angular momentum should be either coming out of the screen or going into the screen, and we decide which direction using what's called the right-hand rule. Now we're gonna discuss something very important about angular momentum, and that is angular momentum in Newtonian gravitational force is constant, is conserved. It's a constant of motion. It doesn't change. Now to prove this, you all know that if you have a quantity that's constant, its derivative will be zero. So let's prove that the derivative of angular momentum with respect to time is zero. Now physically this is called the torque that's responsible for changing the angular momentum. So let's prove that torque is zero. Now the derivative of angular momentum means the derivative of the cross product r cross p. Now you should know that from vectors that the derivative with respect to time of two vectors that are multiplied by each other, cross product, then that derivative is equal to the derivative of the first vector dr by dt cross the second vector p plus the first vector cross product with the derivative of the second vector. Now let's check those two terms and prove that the answer is zero. Let's look at the first term. Now the derivative of r with respect to time, well, that's just the velocity of the object. Now velocity is parallel to linear momentum p, and we all know that the cross product of two vectors that are parallel is just zero. So the first term should vanish, is equal to zero, because the velocity, that's the derivative of r with respect to time, is parallel to the vector linear momentum p. Now let's look at the second term. R vector cross the derivative of linear momentum with respect to time. Now remember that the derivative of linear momentum with respect to time is just the force, according to Newton's second law. So that's just the force. But the force of gravity is in the same direction as R vector. They are parallel. So R vector and the force are in the same direction, and so the cross product is 0. And here we prove that the derivative of angular momentum with respect to time is 0, which means angular momentum is conserved. Conserved means it's constant of motion. It doesn't change with time. And that's an important result in our case. Now let's continue to discuss what is the meaning of this. Now we all know that if a vector is constant, then this means its magnitude and its direction are both constants, do not change. So let's look at the direction of angular momentum. Now, since the direction of angular momentum is constant, which means it doesn't change its direction, and we already know that the direction of angular momentum is perpendicular to the position vector and velocity. So angular momentum is perpendicular to the plane of motion. But since that direction is constant, so this means the plane of motion is constant. And that means that the object will move in a fixed plane. So the motion is two-dimensional. So here we conclude a very important result, saying that objects under the force of gravity, according to Newton's law, will move always in two dimension at most. We don't need to discuss 3 dimensions of this problem. So this problem only will be discussed in 2 dimensions. And that will simplify a lot the discussion of motion under Newtonian gravitational force. Now, the magnitude of angular momentum is also constant. Now, because the angular momentum is just a cross product between 2 vectors, so we know that its magnitude is equal to the magnitude of the first vector, which is r, times the magnitude of the second vector, which is linear momentum, and that's just the mass multiplied by the speed. But then also we have another term, that's sine theta, sine the angle between the 2 vectors. Now think about v, the speed, times sine theta. Now this is the component of velocity that is perpendicular to r. Or you can think of this as the rotational component of velocity. So velocity in 2 dimensions has 2 components, because it's just 2 dimensions. One component will be along r, and another component will be perpendicular to r, and that's the rotational component of velocity. So now, what can we learn from this video, from the discussion so far? Let's take the special case where angular momentum could be 0. And this would happen if the 2 vectors r and momentum or velocity are in the same direction. In this case, the angular momentum will be 0, so there will be no perpendicular component of velocity. And that means the velocity is simply in the direction of r. Now that's what is called in many elementary textbooks as free fall. So the object will move along the line r, and that's just motion in 1 dimension. So one possibility, a special case of motion under Newtonian gravity, is 1-dimensional, and this will happen if the angular momentum is 0. Now, since angular momentum is constant, which is 0 in this case, so it will remain 0, and the object will keep moving along r. It could go far along r, or it could come back in the opposite direction, closer to the origin. Still, both cases, angular momentum is simply 0. Now, the second general case is where angular momentum is not 0. And this will happen when we have a perpendicular component of velocity. Now, in this case, because of this component of velocity, the rotational component, motion will be 2-dimensional. and the object will keep moving in the same plane forever. Now we notice that because the angular momentum is not zero, so the perpendicular component or the rotational component will never be zero at any other time. So the object will always have this component of velocity. Another comment we can make is that when the object is far away from the origin, so that's when r is big, then the rotational component of velocity will be small. So this means the rotational speed of the object will be little. When the object is closer to the origin, so that's when r is small, then the rotational speed will be higher or larger. So that's another important comment to conclude about motion under Newtonian gravity. Thank you for watching this video, and we'll see you in a new video where we will talk about another conserved quantity, that's energy. Thank you for watching.